Back to a new video. In this video, we will be solving the physics Heykel. So I'm going to cover the whole main ideas of the Heykel for year 2023, term 2 in physics. I make this video more interactive by including Classkick activity. So you are free and welcome to join the Classkick and drop this class code and try to solve the questions there. Also, there is another logo. Every time you see this logo on the slides, so this is mainly for multiple choice questions. So every time you see this logo, you are free to put your guess in the comment box. And here we go with the first slide here. I will give you a main idea about what the exam, physics exam would be. So it's mainly divided into three parts. Part 1, Part 2, and Part 3. So Part 1 includes 6 questions. It's a multiple choice questions. So mainly these questions are so easy. It includes definition or units of some parameters. It's so easy. Part 2, it's a little bit more challenging. It includes some equations, but it's still easy because it's one-step verification. And also, it's a multiple choice question. Part 3, it's the written part. It's made for 4 questions. Each one of them is on 5 marks. So in total, the exam it includes 20 questions. It's all over 100. And still with 2 questions, 2 bonus questions. Each one of them is over 5 points. So the total time of the exam is 120 minutes. It's 2 hours, and calculator is allowed. So here we go with the first question or the first idea. So it's about section 5.1, the current and charges. So what's the asking? Show that the definition of the electric current is related to the net charge. So we need to define the relationship between the current and the charge through the equation between current and charge related to time. So of course you need to remember this equation where I, the current, is equal dq over dt. It's the derivative of the charge over delta time. So the unit of the current, which is ampere A, and the unit of the charge Q is C, and of course the time is in seconds. You can verify this on page 117. With the next slide, here it's about the current density J. So we need to define the current density J as the current per unit area flowing through a conductor. So here we have a wire. The flow of the current, the flow of the charges through the area of the wire is considered as the current density J. So J is equal to the current over A. Here A stands for the area. Look here in the picture, that's the cross-sectional area of the wire, which is in this case pi r square. With the next slide, third point, recall that and apply Ohm's law. Of course, Ohm's law, the famous law where V, the voltage, is equal to the current I multiplied by the resistance. And you can arrange the equation, it depends on the given. Here we are with the next slide. It's about resistivity and resistance. You can find that on page 123. So the resistance is equal rho, which is the resistivity, multiplied by L, which is the length of the wire, over again the area, which is the cross-sectional area of the wire. And also in this case, it's pi r squared. So that's the first bullet number 4. It's about the resistivity. We continue. Here is another. Here is an application for this law. So I invite you to go to Classkick and drop your answers there, and inshallah I will be checking your answers and correct it. So what's the resistance of a copper wire of length L, diameter D, the resistivity of the copper is 1.72 by 10 to the power of minus 8 ohm per meter. So you need to calculate the resistance R. Hopefully in 2 days, on Thursday, I will making another video where I explain these questions. So slide number 8. So it's about electromotive force and Ohm's law. So you should know that you should know how to define the electromotive force, which is mainly the battery, as the potential difference. So EMF is the battery, supplied by the battery or a device. Okay, and and bullet number 6 is to identify that at least one component in a circuit must be a source of EMF. So EMF or the battery is like the heart, where the heart is pumping the blood into the body. The battery also is pumping the charges into the wire. So there is no wire without a battery. So the battery is essential part or component of the whole circuit. Here is a question about it. So which of the following has the same unit as the electromotive force EMF? So you are free now to stop the video, think about this question and drop your answers in the comment box. So what do you think the answer is? A, B, C, D or E? So please write the number of the question and beside it your answer, A, B, C, D or E. We continue the next slide. So here also you are free to solve this question on Classkick. This is slide 2 on Classkick. So we have two resistors, R1 and R2, are connected in series with a battery and an ammeter, as shown in the figure here. The battery supplies the circuit with a 8 volt, and the ammeter has a resistance of 1 ohm. So the resistance of the ammeter is 1 ohm. So asking what is the current? So what do you think the current is? So I invite you to go to Classkick and try to solve this question. Again, I remind you, after 2 days, hopefully, I will be solving these questions in a specific video. So we continue. Here is the bullet number 7. It's about mAh. So this stands for milliampere per hour. So how to convert from milliampere per hour to coulomb? So you always need to multiply by 3.6 because 1 milliampere per hour is equal to 3.6 coulomb. So this is a unit of charge. Milliampere, remember the ampere, the current multiplied by time, is Q, the charge. So 1 milliampere per hour is equal to 3.6 coulomb. We continue. So here is a question. Suppose a AAA battery, so this is what we call by AAA battery, is able to supply 625 milliampere per hour before its potential drops below 1.5 volt. The question is how long it will be able to supply power to a 5-watt bulb. So how long means we need to find out the time. So what that's given in the question is the charge Q, the delta V, which is 1.5 volt, the power, and they ask for the time. So what equation in this chapter that connects all these together? Yes, so we need to use this equation, of course. So where Q, the charge, is equal I multiplied by delta T. We discussed this in the third slide. And there is another equation also that we need to use it to solve this question, where I is equal to power over the voltage. So I have to replace or put equation 2 and drop it here in equation 1. And that's what we have. So Q now is P over delta V multiplied by delta T. So you arrange the equation. Delta T now is Q multiplied by delta V over the power. So Q is given. Remember here, Q, which is in milliampere per hour, you have to multiply it by 3.6. Then multiply it by the voltage, which is 1.5, over the power, which is 5 watt. So it needs it needs 675 seconds. We continue with bullet number 8. So identify that the same current flows through a set of resistors connected in series. So here we are talking about a circuit where the resistors are connected in series, like here, like this picture. So all of them, of course, have the same current. I1 equal to I2 equal to I3. Due to the fact that the electric charge is conserved, of course, calculate the equivalent resistance of resistors connected in series. So how to connect the resistance in a series circuit? Of course, you need to add all the values, R1 plus R2 plus R3. Here is a quick example or quick question about it. And also, I remind you to drop your answers in the comment box. Please don't forget to mention the number of the question, 25.4. So here we are the question. So three identical resistors R1, R2, and R3 are wired together as shown in the figure. So they are in series. An electric current is flowing through the three resistors. So what is the current passing through R2? So what do you think the answer is? Is it the same? Is it the third? Is it twice? Is it 3 times? Or cannot be determined? What do you think of that? Drop your answers in the chat box. Here we continue with the number 9. We need now to calculate the current, the voltage, and resistance for circuit arrangements containing resistors in series and parallel. So also here they include the parallel circuit. So we need to calculate the equivalent resistance for resistors in parallel. So what do you think, or how to calculate the resistance, the total resistance in case of parallel circuit? Yes, of course, we need to apply the inverse relationship where 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Of course, in case of a series parallel, or everywhere the current is the same. But in case of a parallel circuit, the total current is the sum of the current passing through the first branch plus the current going through the second branch plus the current going through the third branch. So I total is equal I1 plus I2 plus I3. We continue with this question. So three identical resistors R1, R2, and R3 are wired together as shown in the picture here. So they are in parallel. They are set in parallel. So an electric current is flowing from point A to point B. So what do you think about the current going through R2? Remember, these three resistors are identical. So what do you think about the current? Is it the same, the third, twice, 3 times, or cannot be determined? So you can drop your answers in the comment box. So we continue with bullet number 10. It's about energy power in its electric circuit. So for the power, we have three equations. The power could be the current multiplied by the voltage, or the current square multiplied by R, or delta V square over the resistance. So we need to show that the power delivered to an electric device is equal to the current passing through the device multiplied by the potential difference across its terminals. So we need to use this equation where power is equal I delta V. Let's solve this question. So if the current through a resistor is increased by a factor of 2, so you increase the current or you multiply the current by 2. How does this affect the power? So what do you think about the power? So which equation connects the power and the current? Yes, that's the equation where power is equal I delta V. It's equal I square multiplied by R because it's energy dissipated. So we need to use the resistance. So they said that the current increased by a factor of 2. So we need to multiply the current by 2. So it's 2I square now multiplied by R. It's because we multiplied by 2 according to what they ask us to do. So it's 2I squared multiplied by R. Because of the square and the 2, so it's 4 times. So of course, it increased by a factor of 4. So if you double the current, the power will be multiplied by 4. And that's the reason. We continue with idea number 11. We are talking about Kirchhoff junctions rule. So the sum of the current entering a junction must equal the sum of the current leaving the junction. So here we have a concept check 6.1 where we have this junction. So what do you think the answer is? Okay, let's discuss the picture first. So we can see that we have 4 currents entering or leaving the junction. So let's count first the currents that they are entering the junction. So yes, I1, I3 and I4 are entering the junction. As you see here, I1, I3 and I4. But what about I2? Yes, I2 is leaving the junction. So we can write according to Kirchhoff junction rule that plus 1 plus I1 plus I3 plus I4 minus I2 because minus I2 because I2 is leaving the junction. The sum of all of them must be equal to 0. And this is equivalent to answer B, where I1 minus I2 plus I3 plus I4 is equal to 0. We continue with the next idea. Here also explain the conventions. This is very important. So explain the conventions used to determine the sign of potential differences around a single loop circuit containing several resistors and sources of EMF. So talking about the resistance and the batteries. Given the assumed direction of current and the direction of analysis, analyze single loop circuits containing 2 sources of EMF and circuit elements. So of course there is a question on Classkick regarding this bullet, but let's discuss the conventions first. This is a very important idea before we go through Kirchhoff rule. So let's set the ideas first. Let's talk about the loop. So let's consider I'm taking this direction of the loop. Let's start with the easy one. So this is the direction of the loops that I define it. It's counterclockwise, and as you see the loop is leaving the battery, VMF. It's the battery, and the loop is leaving the battery from the positive side. You can see it's positive. So in this case, well, while we are writing the equation, we write plus V. But on the other hand, if the loop is leaving the battery from the negative side, you put minus V. That's how we write the equation. It's minus V. What about the resistance? So if the loop you are taking is in opposite direction of the current, again I repeat, if the loop taken is opposite direction of the current, so then it's positive because it's in the opposite direction. If both the loop and the direction of the current both have the same direction, so then you have to include the minus. So that table is equivalent to this to the sign convention here. So it's the same where where both have the same direction as the loop, so you need to include minus. And if the loop is the same as the direction or leaving from the positive side of the battery, then it's positive. Let's apply this. Let's do a application on that. So this is a picture of a circuit. Then I choose this direction of the loop. It's going that way. It's counterclockwise. So we need to apply Kirchhoff rule to a single loop circuit. So that's the case. What do you think the equation is? Yes, it's plus VMF2. Why it's plus? Because as I told you, the loop is leaving the battery from the positive side, and then it continues through this way, but the current is opposite to the loop. So what? So we need to put plus. So it's plus I R2. We continue, the loop will continue this way. Also here it's opposite to the direction of the current, so we need to have plus IR1. We continue, the loop continue here and go to this battery. Here the loop is leaving from the negative side, so you have to include minus VEMF1. All of them are equal to 0. Next slide. Here you have the chance to solve. You have the chance to solve this question on Classkick. It's on the third slide. So where V1, V2 are given, 1.5 and 2.5, R1 and R2 also are given. So asking what's the magnitude of I1. So I'll give you a quick hint. Okay, so you can use the Kirchhoff loop law, and that's the hint. You can consider that's the direction of the loop and that's the direction of the current. Okay, so I'll give you the chance to solve this, and then as I told you, after 2 days I'll go through the correction. So here we continue with this question. Also you have the chance to drop your answer in the comment box. So here 6.2 concept check. In the circuit, in the figure, there are 3 identical resistors, R1, R2 and R3. The switch S is initially opened, as you see here. When the switch is closed, so when we close the switch, what happened to the current going through R1? So what do you think about the current? It will decrease, increase, or stay the same? What do you think? So just put the number of the question, and is it A, B, or C? We continue with bullet number 15. Solve problems on Wheatstone bridge. So Wheatstone bridge are interesting circuits in electricity. So in this question we have to determine the value of Ru. That's Ru. You can find this on page 151. So Ru where the or is the unknown. So the known resistances are R1, which is 100 ohm, R3, which is 110 ohm, RV, which is equivalent to Ru, which is here 15.63 ohm. So the current through the ammeter is 0. So here the current, that's what makes Wheatstone bridge special. The current going through the middle way where the ammeter is must be 0. So what do you think the current of Ru? So you need to apply the equation where Ru is equal. You need to make the division between the two resistances that are on the other side. So R1 divided by R3 multiplied by RV. So that's what we did. R1 divided by R3. So R1 divided by R3 multiplied by RV. And that would be the value of Ru. It's 14.2 ohm. We continue with number 16. We need to recall that the ammeter is a device used to measure the current. So ammeter is used to measure the current, of course, and the voltmeter is a device to measure the potential difference V. So one important idea to consider here, ammeter is always wired in series. Ammeter never wired in parallel, always in series. What about the voltmeter? Voltmeter is the opposite, must be wired in parallel. The voltmeter always supposed to be wired in parallel, as you see here. So voltmeters are wired in parallel, however, the ammeter must be wired in series. So I'll give you the chance to solve this question. 6.4 concept check. So we have 3 different circuits. Which one do you think, which of the circuits shown will not function properly? So what do you think? Which circuit will not function properly? Is it A, 2, 3, or 1 and 2, or 2 and 3? So give it a try by dropping your answers in the comment box. We continue with charging a capacitor, important equation. So we need to apply the relationship giving the charge as a function of time, that's the charge Q function of time, for a capacitor in a charging RC circuit. So in case of RC circuit, that's the charging equation, where Q, the charge, is equal C, the capacitance, multiplied by the voltage, all of that multiplied by 1 minus exponential of minus t over RC. And you can find this equation on page 156. Also, I'll give you the chance to solve this question where we apply the previous equation. So this is on slide 4 on Classkick. So an uncharged capacitor C, 14.9 mu farad, a resistors of R 24.3 kilo ohm, and a battery of 25.7 volt are connected in series. What is the charge? So what's the charge Q, where the time is given? Time is 0.3621 seconds after the switch is closed. So give it a try. Of course you... so the question... So in the previous slide, the answer must not appear. Maybe a mistake. Okay, 7.1 permanent magnets. Anyway, give it a try on the Classkick, please. So here we are with bullet 18. Recall that the magnetic field is represented using field lines. So for the magnetic field, we have field lines. Identify the properties of a magnet. A magnet always has a north pole and a south pole. So as you see here, even if we break a magnet, the south and the north pole will regenerate again. We cannot separate the north from the south. Okay, so even if we cut the magnet in half, or by keeping cutting the magnet, N and S will always regenerate, cannot be isolated. So that's the word. The poles in a magnet cannot be isolated. They always come in pairs. They are in couple that cannot be separated. Opposite magnetic poles attract and like magnetic poles repel. Of course, as you know, if two poles are the same, so they will repel. If they are in opposite, NS, for example, they will attract. Breaking a bar magnet in half results in two new magnets, each with a north and a south pole, as we discussed earlier on. So magnetic field lines originate from north, always start from north. The lines always start from north and finish and terminates in the south pole. So it starts with N and finish in S. We continue. Here bullet 19 and 20. Solve problems on multiple loops circuits. So we are back to Kirchhoff. Express Kirchhoff rule mathematically and apply problem solving. So here I'll give you another chance to apply the Kirchhoff rule in this circuit to find out I2. So R2, R1, V1 and V2 are given. The question is to calculate I2. So here with the bonus question, we are approaching the end. We are approaching the end of the video. So this is the first bonus question. Recall that the SI unit of a magnetic field is Tesla T. So of course the unit of the magnetic field is Tesla, but let's discuss it a little bit. So remember this equation, F equal QV multiplied by B. Do you recall that? So if we discuss, or let's focus on B, the magnetic field. So after arranging the equation, it would be the force over QV. The force is in Newton over Q, which is in Coulomb. Velocity V is in meter per second. So it's M divided by S. So we have double division. So S will become upward. So it's NS over CM. Okay, so NS or Newton per second over cm, we can write it on the other way, where N Newton over ampere per meter. Why it's ampere? From where A came, so it's S over C. Do you remember this, the third slide where we said that I is equal Q multiplied by T. So here I is equal, the current is equal to Q over S. So replace S over C by 1 over A. So that's the other unit of the magnetic field, N over AM. And here we are with the last bullet number 22. So apply the relationship between the magnetic force F, charge Q, velocity, and the magnetic field B. So we need to find the relationship between all these three parameters. So yes, that's it. It's R, which is the radius. Why we have a radius? Why we have a circular shape here? Because the charged particle is entering a magnetic field. Every time a charge enters a magnetic field, it goes through a circular motion. So here we have R, which is the radius of that path, is equal m, which is the mass of the particle, multiplied by its velocity, over q, the charge, multiplied by the magnetic field. So let's apply this to an equation. So also you have the chance to solve this question. So the Earth is showered with a particle from space known as muons. So mass of the particle is given, magnetic field, the velocity also is given. The question is to calculate the radius of the orbit. You have to calculate the radius. So give it a chance to solve this question. So this is the given, and that's it. We finish discussing the whole bullets of the Heikal. Remember, I will in 2 days, inshallah, I will be, yeah, in 2 days, inshallah, I will be going through the questions on Classkick, making a special video for Classkick. And thank you for watching. Thank you for your attention. Oh, I forgot to tell you, in the description, I will put the link for Telegram, as you can join and find this PDF there. Wish you full mark on physics.